So first thing, we're gonna start, ouch, with our pictures. Smashed my finger in my chair. And yesterday, so the top two pictures are gonna be the same as yesterday. Mainly because I wanna get the idea in your head, like get it really stuck in there. The bottom two are different. So yesterday, Casper's playing with my lights again today. Yesterday, we looked at the A and B picture for mutually exclusive, A or B for mutually exclusive. Today, we're gonna look at the picture A and B, and they're not gonna be mutually exclusive. Same thing with A or B. So like I said, top two are the same. I really just want to get the ideas in your head. Get them stuck in there forever and ever and ever. So remember, we always draw a box, sample size. So we sample space. So we label it with an S. Complement picture. So here's A. Here's a complement. Everything outside the circle A is the complement, A not happening. And just as a reminder, probability rule number 1, probability of A complement is 1 minus the probability of A. Then we have our mutually exclusive events. So we have our box. We label it with S so we know it's the sample space. We have event A, event B. They are mutually exclusive because they can never happen at the same time. Outside of A and B, so all this stuff outside the two circles, is A complement and B complement. So A not happening and B not happening. And our second probability rule came from mutually exclusive events, and that told us that the probability of A or B was the probability of A plus the probability of B. Oops, forgot my parentheses. Now today we're going to focus on events that could happen at the same time. So non-mutually exclusive. So for A and B, we have our sample space. Here's event A. That's a really bad A, sorry. Event B. And A and B, remember the alternate notation and. That symbol, I told you yesterday, means intersection. And so when we're asked to find the probability of A and B, that means we need to find this little overlap. That is A and B. Outside our two circles is A complement and B complement. A not happening and B not happening. And then our last picture, A or B, when they are not mutually exclusive. This is going to be the Starbucks idea. So we talked about I can't remember the restaurant we went to, and we talked about if you order a hamburger, they ask you if you want French fries or a salad. And that means you can get French fries or you can get a salad. You can't get both without having to pay extra. But when you go to Starbucks and you order a black coffee, the barista says, do you want cream or sugar? And that means we could get cream, or we could get sugar, or we could do both. So when we are looking at A or B for non-mutually exclusive events, that means we're looking at this whole double circle thingy. We're looking at the probability in A. We're looking at the overlap stuff in the middle. And we're also looking at all of this stuff where it's just B. And the alternate notation, that symbol, just as a reminder, means union. And I almost forgot to put my S for sample space. And then same thing, outside the two circles is what is known as A complement and B complement. So we're going to be focusing on cream or sugar today and finding that probability. We'll do this because to find cream or sugar, we have to know the overlap in the middle. But this is going to be the focus. Any questions before I move the paper up? All right. We're going to start out with cards because, well, it's me. Can you guys tell I played a lot of poker as a kid? My parents taught me poker. Lots of different poker games. I know a lot of them. My least favorite, though, is Texas Hold'em. I don't like Texas Hold'em. That's probably the most popular one. All right, back to math. So we're working with our standard deck of playing cards, and we're going to deal a single card. So we have two events, J, which means getting a jack, and R, which means getting a red card. Now, I told you, I think at the beginning of this unit, I can't really remember though, that we were gonna learn different strategies for helping us find probability. Venn diagrams are one of them. Two-way tables is another. We're gonna learn tree diagrams, and I feel like I'm still forgetting one, but I don't know. So anyways, we're gonna learn how to make a two-way table. And we're also, in the next example, gonna use a Venn diagram. And then my last example, we're gonna do both so that you can see no matter what the problem is, you can use both. So hopefully you figure out which one you prefer. In your homework tonight though, it will specifically say two-way table or Venn diagram, and I want you to try doing both because watching me, you may have a preference, but when you actually try it, you may have a different preference. So, two-way tables, we've worked with them before. Last unit when we did marginal and conditional distribution, we used two-way tables. So we're going to have one of the events and its complement across the top of our table. We're going to have one event and its complement going down this side. And then we also have to remember to have a total column and a total row. So like a super extra large tic-tac-toe, I suppose. Makes me think of the game Connect 4. Because if we tried to play tic-tac-toe, we'd have to get 4 in a row. just 30. Anyway, sorry. So like I said, we're gonna have an event. So I'm gonna go with J. Doesn't matter, I could put J there. I'm just doing it this way. And then it's complement, so J complement. Across the top, down the side of the other event, so R red card and R complement. We want to have total, because remember on the two-way tables, first thing we did was find the totals, so what we would know what to divide by. And then that means that down here in the bottom right is our grand total, which, since we're inputting the numbers into the two-way table, the grand total is extremely important. So we're working with a standard deck of cards. What is the grand total number of cards in a deck? Anybody remember? I tried to beat it into your head the last 2 days.
52.
52, thanks. Bailey, I saw your hands right as he started speaking. 52. And then we're gonna fill in the table. So I'm gonna start with J. J means getting a jack. How many total jacks are in a deck of cards? Thanks, Nate. 4. So if we have 4 jacks and we have 52 cards total, how many cards are not jacks or J complement? Four plus what? Oh, thanks, Nate. 52, so 48. So we have 4 jacks, 48 not jacks, 52 cards total. R is red. How many red cards do we have in a deck?
26.
Yes, Chloe, 26. And if 26 are red, that means how many are not red?
26.
26. Thank you, Chloe. So then in this cell, I need to know the number that are jacks and reds. So how many of my jacks are red cards? If we have 4 jacks total, how many of them are red? 2. Thank you, and Chloe and Nevaeh. So if 2 are red, that means 2 jacks are not red, right? 2 plus 2 is 4. How many of my red cards, there are 26 of them, 2 of them are jacks, so how many are not jacks?
24.
Thanks, Chloe. And how many non-red, non-jack cards do I have?
24.
Thanks, Chloe. And we filled in our table. Now we're going to use that table to answer some probability questions. So the first one says find P of J and P of R. So probability of J. So I'm going to look at my total divided by my grand total. So the probability of J is 4 out of 52. Which, if I simplify that, that's 1/13. I'm going to leave it like that. You can use decimals if you want. In this case, I'm going to leave it like that. With cards, I like to leave them as fractions. Probably because mainly they usually tend to be not pretty decimals. But and then we want to find the probability of R. So go to the total number of red cards out of the grand total. So 26 out of 52, which simplifies to 1/2. So if you want to use a decimal here, I know that one. I know most of my fractions to decimals, but I don't know 1/13. And I'm not even going to try. All right, part C, describe the event J and R in words. So if your friend was looking at your stats homework and they were like, what does J and R mean? What would you tell them? What does it mean?
J is being a jack and R is a red card.
So if J is a jack and R is a red card, what is our card we pull? J is a jack, R is red, so our card is... I just want you to rearrange them. A red jack. I don't know why, I suppose because it's the English language. We say the color first. So when we are trying to find J and R, we want to figure out red jack. So then it asks us to find the probability of J and R. So red jack. If I go up to my table, there are 2 red jacks out of 52 total cards. And that would be 1/26 simplified. Now we're going to find the probability of J or R. So the probability of the card is a jack, red, or a red jack. So, sorry, I'm picking what color I want to write with. We want to find the probability J or R. Does anybody have any predictions for me about J or R? What's the probability? It's a jack, a red card, or a red jack. No thoughts? Nobody? Okay. Well, yesterday we learned that the probability of J or R would come from the probability of J plus the probability of R. Probability of J, 4 out of 52. Probability of R, 26 out of 52. Which would give me 30 out of 52. Now, I kind of gave it away if you read. I said, explain why P of J or R does not equal P of J plus P of R. So what I showed is incomplete. It is the start of how I find it, but if I left it here, I would get the wrong answer. So when I find the probability of J getting a jack, I looked at 2 red and 2 non-red jacks to get 4 out of 52. When I looked at the probability of a red card, I looked at my 2 red jacks and my 24 red non-jacks to get a total of 26. Notice that this cell shows up twice. I counted it in this 4, 2 plus 2 is 4, and I counted it in this 26. 2 plus 24 is 26. So I ended up counting my red jacks twice because I counted them in the number of jacks and I counted them in the number of red cards. So when our events are not mutually exclusive, to find the probability of J or R, I need to take the probability of J plus the probability of R and subtract the probability of J and R. So that gets rid of one of these because I counted it twice. So we're going to subtract 2 out of 52. So 4 plus 26 is 30, minus 2 is 28. So the probability of J or R is 28 out of 52. That they're both divisible by 4, so 7/13. And that leads us to rule number 3, the general addition rule for any 2 events. So you could use this rule with mutually exclusive because if J and R were mutually exclusive, this would be 0. So we would be subtracting 0, which wouldn't affect our probability. So if you want to memorize this one, you can use it for any 2 events. Or you can remember that if they're mutually exclusive, you just add probability of A and B. And if they're not mutually exclusive, you add the probability of A and B, but subtract their intersection. And just so we have the alternate notation, probability of P or B Casper's bag. All right. So that's probability rule number 3. Any questions before I move on to our next example? This time we get to use a Venn diagram. What? I personally like Venn diagrams a little more. Call me weird. I don't know, there's just something kind of satisfying about making a Venn diagram correctly. Sorry, I have to sneeze. All right, so this time we're looking at an apartment complex. 40% of the residents read USA Today, 25% read the New York Times, 5% read both. We're gonna pick a resident of the apartment complex at random and record which of the 2 papers the person reads. So we're going to construct a Venn diagram to represent the outcomes. We're going to find the probability the person reads at least one of the 2 papers, and then we're going to find the probability that they don't read either paper. So we're going to make our box first. Oh, before we do that, we should probably define our events. So 40% read USA Today, so I'm going to define event U to mean they read USA Today. Um, 25% read the New York Times, so I'm going to use N to mean they read the New York Times. So then I have letters to represent my events when I draw my Venn diagram. So I'm going to put my Venn diagram in a box so that I know I'm covering all possible outcomes. It's my sample space. I have event U, and I have event N. Now, anytime you make a Venn diagram, you want to start with the overlap. So if we go back up to our paragraph, it tells us 5% read both. So that is the number I'm going to start with when I fill in my Venn diagram. 5% as a decimal is 0.05. I suppose you could leave it as a percent. I tend to change them to decimals. Then we are told that 40% read USA Today. So I need 40% in my circle U. I already have 5% of those people. So that means that I need to have another 35% to make sure I have my 40% that read USA Today. 25% read the New York Times. So in circle N, I have to have 25%. I already have 5%, which leaves 20%. So then I'm going to find the probability that the person reads at least one of the two papers. What does that phrase mean? At least one of the two papers. Nobody? I suppose because it's Friday, I'll be nice. So at least one of the two papers is kind of like the cream or sugar. So they could read USA Today only. They could read New York Times only. Or they could read both. Because at least means one or more. And in this case, since there are only two options, it means one or two of the papers. So it's asking us to find the probability that they read USA Today or they read the New York Times. And we just learned the rule to find that. We're going to take the probability that they read USA Today plus the probability they read the New York Times minus the probability that they read USA Today and the New York Times. So the probability they read USA Today, 40%, or if you look at the circle U, 35 and 5 is 40%. Plus probability New York Times, 25%, or circle N, 0.05 and 0.2 is 0.25. And then we subtract the overlap because we counted it twice, which is 5%, or it's up here, 5%. So 0.4 plus 0.25 is 0.65, and 0.65 minus 0.05 is 0.6. So the probability they read USA Today or they read the New York Times is 0.6 or 60%. Then we want to find the probability that the person doesn't read either paper. They don't read USA Today, they don't read the New York Times, They don't read both. They don't read, well, I guess I can't say they don't read, but probability, U complement, they don't read USA Today, and N complement, they don't read the New York Times. So we have a complement problem, which means we can use rule number 1. So 1 minus the probability they read USA Today or they read the New York Times. That's a bad symbol there, sorry. And we just found this, that's 0.6. So 1 minus 0.6, which is 0.4. So the probability they don't read either paper is 0.4. Now, if we go back to our Venn diagram, not reading either paper would be all this stuff on the outside. So we had 0.35 and 0.05, that's 0.4, plus the 0.2 is 0.6. So we have 0.6 in the middle here, which leaves 0.4 to be outside here because our sample space has to add to 1. And this stuff out here is U complement and N complement. Not reading USA Today and not reading the New York Times. Any questions before we get to our last example? No? All right. So like I said on this last one, we're going to do both a two-way table and a Venn diagram, just to kind of show you that you can do either when you're given the information. This example says that in December of 2008, it was found that 78% of U.S. households had a traditional landline telephone. Anybody still have a landline? No? Okay. 80% had cell phones, 60% had both. So we're going to make a two-way table. We're going to make a Venn diagram. Then we're going to find the probability that they have at least one of the two types of phones, and then find the probability that they have a cell phone only. So two-way tables like a giant tic-tac-toe, 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 sorry. A very strange person. Those of you that have had me before, you know that. All right, across, before I can put labels on there, I gotta define my events. So 78% have a landline. So I'm gonna use L to mean landline. 80% have a cell phone, so I'm gonna use C to mean a cell phone. So we have L and L complement, C and C complement, and just because I'm feeling lazy because it's Friday, I'm not going to spell the word total. I'm going to abbreviate it as TTL. Now, on this example, we're given percents. So when we fill in that grand total down here, what should all our percents add to?
100.
Thanks, Chloe, 100. Now, if you would rather, you could turn all your percents to a decimals and make the grand total 1. I personally leave my percents as percents because I found that I make slight mistakes if I try to turn them into decimals and fill in the table. Apparently I can't multitask. All right, so 78% have landlines, so that would be our total for the landline. 80% have cell phones, so that's the total for cell phones, and then 60% have both. So landline and cell phone would be this one, and we have 60 right there. And then we can use addition to fill in the rest. So 80 plus what would give me 100? 20, thank you. 60 plus what would give me 78? Thanks, Chloe. 78 plus what is 100?
22.
22, thank you. And then 60 plus what is 80?
20.
20. And then last one, 18 plus what is 20, or 20 plus what is 22?
2.
2. Thanks, Chloe. So we made our two-way table. Now we're going to make a Venn diagram. So we're going to make our box first. It's our sample space. And there's landline. There's cell phone. I will never, ever, ever be able to make my Venn diagrams to scale. Sorry. You'll see what I mean in a minute. So remember, I said with Venn diagrams, you always start with the overlap. So they have both landline and a cell phone. That's 60%, so 0.6. That's probably not really 60%, so that's what I mean when I say I can't make them to scale, but you guys get the idea, and that's the important part. And then landline is 78%. I already have 60% of those people covered in this overlap, which means I have 0.18 outside the overlap, but still in circle L. 80% have cell phones. I already have 60% of those people, which leaves 0.2 to be in circle C, but outside the overlap. And then, because I told you on the previous one that we should make sure our numbers add to 1, we need to see what percent is outside our two circles. So 0.18 plus 0.6 is 0.78 plus 0.2 is 0.98. So that would mean we have 0.02 outside here. And that would be L complement and C complement. No landline and no cell phone, and apparently no connection to the world. Any questions on the two-way table or the Venn diagram before we get into our last two questions? All right, so find the probability that they have at least one of the two types of phones. So up above, we talked about what at least one means. So that could be one of the types or two of the types. So landline or cell phone or both. So we want to find the probability of L or C. And we have our general addition rule that tells us we take the probability of L plus the probability of C minus the probability of L and C. Probability of L, 78%. You see it here in the table. Or if you look at all of circle L, 0.18 and 0.6, so 0.78. Probability of C, 80%, right here in the table, or all of circle C, 0.6 and 0.2 together, which is 0.8. And then minus L and C, which is 60%. That's right here in the table, or that's the intersection in the Venn diagram. 0.78 plus 0.8 is 1.58. Minus 0.6 is 0.98. So the probability that they have a landline or a cell phone is 0.98. Sorry, I don't know how I didn't make that on a straight line. And then our last question for today is find the probability that they have a cell phone only. So probability they have a cell phone and no landline. So in the two-way table, this one is pretty clear. Cell phone, no landline. It's 20%. It's in the Venn diagram, but it's not quite as clear. So we want cell phone, which is this whole circle, but we don't want those that have the landline, so that means we're only looking at this crescent moon part. They have a cell phone, but they don't have the landline. So it is in the Venn diagram, but it's not necessarily quite as clear. So this would be 0.2. Questions?